You're struggling to see the difference.
So today we're talking about concavity. The graph of a differentiable function y equals f of x is concave up on an interval I if y prime is increasing on I. This is not the original function increasing. This is the derivative increasing. I want to make that distinction. When y prime is positive, our original function was increasing, but now I'm talking about the derivative increasing. That means my tangent slopes are not only are they well, they don't necessarily have to be positive, but what they're doing is they are increasing, meaning your tangent slopes are getting steeper and steeper and steeper. Okay? Even if they're negative, then that means they're increasing, they're getting closer and closer and closer to zero. So what we end up with, concave up, looks like kind of like a smile, sort of. Concave up. A function is concave up if the derivative is increasing. Likewise, it's concave down on an interval I if y prime is decreasing on I. Sad face. It has nothing to do with the original function. This is the graph of the original function, though. The original function may be decreasing or increasing for it to be concave up, or vice versa. It may be increasing or decreasing. It's the derivative. Are my tangent slopes, if they're negative, are they getting closer to zero? Or if they're positive, are they getting steeper and steeper? Or are my tangent slopes decreasing from, they're positive, but they're decreasing towards zero? Or they're going further and further in the negatives. Your grades in this class probably are concave up, aren't they? They went down at first, and now hopefully they're going back up. I don't even know why I thought of that. All right. Anyways. All right, we have a concavity test. Which will lead us towards the second derivative test. But the graph of a twice differentiable function y equals f of x is concave up on an interval where y double prime is greater than 0. If the second derivative is positive, the function's concave up. Second derivative tells us concavity. That's where we're headed with this. We finally have a reason for the second derivative, not just Mr. Crabtree wanting to torture you with having to use your derivative rules twice over.
I'm sure about that.
I make such a convincing argument, don't I? I should have been a lawyer. All right. Concave down, as you can imagine, on an interval where y double prime is less than 0. All right, so let's look at an example. An example. Let's determine the concavity of the function on the given interval. In our first function, we'll choose an easy one to start with, right? Y equals x squared on the interval 3 to 10. Let's find the derivative. The derivative would be 2x, right? Let's find the second derivative. 2. Oh. When is that positive? It's always positive. So guess what? This thing is entirely concave up. Well, isn't it a parabola that's opening up? Because x squared, y equals x squared, that's the parent quadratic function. It's a U-shaped graph that opens up, so yeah, it's concave up the whole time. This is always positive, so y double prime is greater than 0, so therefore, my little 3 dots, therefore, that's what that means. Therefore, y is concave up. I'm going to abbreviate CCU for concave up, but please don't do that on the AP test. On, I guess we should say on the interval 3 to 10. It's actually concave up everywhere, but it'll definitely be concave up on that interval they were interested in. What if instead we did y equals 3 plus sine x. True. On the interval 0 to 2 pi. Love trig.
I don't know.
What's the derivative?
Isn't it, it would be just cosine x, right?
Yeah, it would, because the derivative of the 3 is 0.
Yeah.
So the derivative of sine is cosine.
And then the derivative of cosine x is negative sine, right?
Oh, so it's negative sine x.
How can we tell if that's... Right.
Well, that's a good question. How can we tell where this changes? Well, think about it like this. We need to find our points where, where concavity, if the second derivative is positive, it's concave up. If the second derivative is negative, it's concave down. So it changes when the second derivative is what?
Oh, okay.
No. If I'm changing from positive to negative, what's in between? What's neutral?
0.
0. Okay, so the second derivative, we need to find where the second derivative equals 0. That'll give us our points. They're not really criticals. You could call them, you won't find this term in a book anywhere, but I've heard them called, they're the supercriticals. What? So, supercriticals. Let's find points where y double prime equals 0. So negative sine x equals 0. Well, we multiply both sides by -1. That's still sine x equals -0. So where is sine 0 from 0 to 2 pi? There's only, not counting those points, because those are not included.
Right.
We don't have to count the endpoints here. There's only one place that it is.
And
Sine
that's
is the y-coordinate on our unit circle. Okay, so if we go back and look at our unit circle here, y-coordinate was 0 at 0, yes, but since that's an endpoint, I'm not going to include that. As I go around the circle, the y-coordinate is 0 again at pi, and then it's not again until 2 pi, but that's the other endpoint. So the only point that's supercritical is pi. So that's the only point we have to consider. So we're going to do a sign chart for y double prime here. We got away with not having to do a sign chart there because it was a constant for the second derivative. Okay, but now the second derivative is potentially changing signs. Pi is going to be our one value we're going to use. We don't need to use the endpoints for obvious reasons because they're 0, 2. So how about pi over 2 and 3 pi over 2, the other two quadrantal angles? Where did I pull those out from? I'm using the quadrantal angles because if you go back and remember, sine with the points that we marked off on the x-axis, the period of sine started at 0 and went to 2 pi. That was the period of the sine function from trig. So our between points, those means there, which when I had you go and find those 3 points in between, you found the one right in the middle and then you found the one in between and in between on the other ones. Do you remember doing that? The 5 points? Like you had this one, you had this one, you found halfway in between, you found halfway in between, you found halfway in between. Remember doing that? Okay, essentially what you did is you found 3 arithmetic means in between 2 numbers. I just didn't call it that. My bad. Okay, but that's essentially what you did. All right, well, the obvious choice then was picking the other quadrantals. Between 0 and pi is pi over 2. In between pi and 2 pi is 3 pi over 2 from the unit circle. So what are the values there? If I plug into negative sine x, I'm plugging in negative sine x right here. If I plug in pi over 2, what is Let's find sine of pi over 2, and then we just change the sign of it because of the negative in front. So what is sine of pi over 2? What's the y-coordinate at pi over 2? 1. But that'll be a negative 1 because I'm plugging in. Yeah, so it's going to be negative. And at 3 pi over 2, sine is negative 1, but the negative in front will make that a positive 1. So we change from negative to positive. This is concave down. This is concave up. So we could say that this function is, therefore, y is concave down on the interval 0 to pi and concave up on the interval pi to 2 pi. Period.
That makes sense when you think of a sine function because it goes like that.
Yeah. You have those waves, right? So there's parts where it's concave up, then there's a part where it's concave down, then it'll be concave up. It can't decide. It's bipolar. Questions? That was probably a bad analogy.
It's pretty.
Did you say bad? It was bad?
No,
Oh.
it wasn't a bad.
I thought you said it was
I
pretty
mean,
bad. I was like, ouch.
Sometimes
Yeah,
bad
Shoot
things
Shoot
still
it
make
straight.
sense.
Oh.
I think
All
there's
right.
one.
I hope it made sense. All right. That's how we can determine concavity. And all we have left to do here with this is to talk about the second derivative test itself, which this leads right into it. If I find the concavity at a critical point, see, this is a supercritical point. My points where the first derivative equals 0 might be elsewhere. In fact, they will be. They'll be here and here. At pi over 2, this function, it was concave down. If it's concave down, what do you have there, a minimum or a maximum? A maximum. And if it's concave up, you have a minimum. That's essentially the second derivative test right there in a nutshell. Okay? Now we're going to hash that out into words. My only problem is I have to pause this. All right, so this leads us right into the second derivative test. Disclaimer, I'm now teaching, there's no students here, so that's why I'm not wearing a mask, just so you know if you're watching this video. All right, so second derivative test. The second derivative test says if f prime of c is equal to 0 and f double prime of c is less than 0, then f has a local maximum at x equals c. So if the first derivative is equal to 0, that means the point's critical. But the second derivative is less than 0, that means it's concave down. If it's concave down, that's going to be a maximum point, in other words. If f prime of c is equal to 0, and f double prime of c is greater than 0, then f has a local minimum at x equals c. Okay, it's critical, but it's concave up. Therefore, that's a minimum. And I also want to note here with this that points where the second derivative is equal to 0 are called inflection points. Inflection points. Let me write that. Inflection points. So let's look at an example. Let's say we want to find all local extrema for f of x equals x cubed minus 12x plus 5. Sorry, actually it's minus 5, my bad. Okay. Well, we'll need the first derivative for critical points. So the first derivative, you'll use the power rule on that. You'll get 3x squared minus 12. You'll also need the second derivative. You'll get 6x. So we'll find our critical points. Critical points are where the first derivative equals 0. So 3x squared minus 12 equals 0. Set that equal to 0 and we'll solve that. So we'll add 12 to both sides. We get 3x squared is equal to 12. We'll divide by 3. X squared is equal to 4. We'll square root both sides. And we get x is equal to positive or negative 2. So our critical points are at positive and negative 2. We'll also find our inflection points. Okay, and some of the problems you're going to look at today actually have you go through and find just inflection points. So inflection points are points where the second derivative equals 0. So you set 6x equal to 0, that's at x equals 0. Okay, that's where our concavity changes. So when we do our sign chart, we're going to put our inflection point on there because that's where our concavity changes. And we're going to test out points on either side of that. And since we know that our criticals are positive 2 and negative 2, we can use those as our critical points, or not our critical points. So they are our critical points, but we can use those as our test values on either side of 0. Okay. So if we go in and we do negative 2 into the derivative, or sorry, the second derivative, we got 6 times negative 2. That's going to give me a negative 12. It's negative though. And we put positive 2 in that, we get a positive number. So that gives us a positive value. So it's concave down at negative 2 and it's concave up at positive 2. And if it's concave down at negative 2, that means that we have a maximum there. So we have a local max here. And we have a local min there. Now I made this video after school and I'd already taken the notes. So the picture of the notes are going to look just a little bit different. I go into a little bit deeper explanation on that and actually put it in sentence form for the answer there. So take a look at the notes to kind of see where how that's a little bit different. I went on ahead and worded that. I basically said, okay, there, negative, since at x equals negative 2, f prime is equal to 0, f double prime is less than 0, therefore it's a local max. And do the same kind of thing with the local min at 2. Okay? That pretty well covers the section. And then the problems that you're going to do is on page 219, 7, 17, and 21. Thank you all.